It's May 12, 1995, Boeing Field, Seattle. A 242-foot aircraft sits on the runway carrying something no long-haul airliner has ever carried before. Just 2 engines, not 3, not 4, 2, for flights across oceans, for routes where the nearest runway is 2 hours away, for journeys where a single engine failure means, well, that's exactly what regulators, airlines, and Boeing's own engineers have been arguing about for 6 years. The test pilot advances the throttles. The GE90 engines, each one producing more thrust than 4 747 engines combined, spool up with a sound no one has quite heard before. In the observation tower, Boeing executives watch with $4 billion in development costs on their shoulders. Airlines have orders pending. Airbus is watching. And if this certification flight goes wrong, if they have to shut down an engine over the Pacific and can't make it back, everything changes. But here's what makes this story remarkable. The Boeing 777 wasn't just betting on new technology, it was betting against 70 years of aviation doctrine, a rule written in blood and smoke that said, more engines equals more safety. The question wasn't whether 2 engines could cross oceans. The question was whether anyone would let them. This is the story of how a plane that shouldn't exist rewrote the rules of long-haul flight, and why the answer to "what if an engine fails" changed the industry forever. To understand why the 777 mattered, you need to understand the rule it broke. It's called ETOPS, Extended Range Twin Engine Operations Performance Standards. Pilots had a different name for it: engines turn or passengers swim. Here's the logic, and it makes perfect sense in 1950s thinking. Jet engines fail. Not often, but they fail. So if you're flying across an ocean, you need redundancy. 3 engines mean you can lose 1. 4 engines mean you can lose 2 and still make it to land. The original ETOPS rule was brutally simple. Twin-engine aircraft couldn't fly routes where they'd be more than 60 minutes from a suitable airport. 60 minutes from a runway at single-engine cruise speed. Look at a map. Draw a 60-minute circle from every airport across the North Atlantic. You'll see the problem immediately. Entire routing structures became impossible. London to New York requires island hopping through Iceland and Greenland, adding hours and fuel. Tokyo to Los Angeles? Forget the direct route, you're going via Alaska. For decades, this was simply accepted. Long haul meant 3 or 4 engines. That's how it worked. The Boeing 707, the DC-8, the 747, all designed around this constraint. But in the early 1980s, something shifted. New turbofan engines, the Pratt & Whitney JT9D, the General Electric CF6, were becoming dramatically more reliable. In-flight shutdown rates dropped from 1 in 2,000 hours to 1 in 20,000 hours. Then 1 in 50,000. Airlines started doing the math. A twin-engine aircraft burns roughly 25% less fuel than a comparable 3-engine design. Simpler systems mean lower maintenance costs. 2 engine overhauls instead of 3 or 4. The business case was compelling, but the regulations hadn't caught up. In 1985, the FAA created ETOPS 120, allowing specific twin-engine types to operate up to 120 minutes from a diversion airport if they could prove exceptional reliability. The Boeing 767 became the first aircraft certified under these rules, then 180 minutes, then, cautiously, 207 minutes. Each expansion required exhaustive proof, thousands of hours of flawless performance, redundant systems for everything, hydraulics, electrics, fire suppression, and even then, many in the industry remained skeptical. The 747 dominates long haul, but it's enormous. Most routes don't need 400-plus seats. The 767 is efficient but too small for major trunk routes. There's a gap in the market, and Airbus sees it. The European consortium is developing the A330, a twin-engine widebody specifically designed for ETOPS operations. Modern, efficient, and sized perfectly for the routes airlines actually fly. Boeing's response needs to be decisive, but the company is fractured. Engineers in Seattle have different priorities than the sales team in Chicago. Production specialists in Everett fight with aerodynamics experts about wing design. Airlines want customization that makes manufacturing a nightmare. Phil Condit, then VP of the 777 program, makes a radical decision. They're going to design this aircraft differently. Boeing creates design-build teams, groups mixing engineers, mechanics, pilots, suppliers, and even airline representatives. United Airlines essentially embeds staff in the design process. Cathay Pacific, British Airways, all Nippon Airways. They're not just consulted, they have input authority. A United maintenance chief points out that a hydraulic access panel requires removing 12 other components just to reach it. The design gets changed. An ANA pilot notes that the flight deck layout requires too much head movement during approach. The instruments get repositioned. This is unprecedented. Aircraft manufacturers don't let customers dictate engineering. But Condit's bet is that front-loading these perspectives will prevent costly changes later. And more importantly, it'll create an aircraft that operators actually want, not just one engineers think they should want. The technical gamble, though, is even bigger. Boeing commits the 777 will be a twin, not a trijet with an optional twin variant, not a four-engine design that could be twinned. Pure twin-engine architecture from day one. This decision locks in massive fuel efficiency and simplified systems. But it also means the 777 must achieve ETOPS certification, and not just ETOPS 120. For the aircraft to work economically, it needs ETOPS 180 minimum. Ideally 207 minutes, routes like Dubai to Los Angeles, Singapore to New York, Sydney to South Africa. These require crossing vast stretches of ocean or remote terrain where diversion airports are sparse. The engineering challenge is staggering. Every system needs triple redundancy. Every failure mode needs a backup. The engines need to be so reliable that an in-flight shutdown becomes a statistical anomaly. And Boeing needs to prove all of this before the first revenue flight. When General Electric started designing this engine in 1990, they faced a problem. The 777's wing was sized for efficiency, which meant the engines had to produce enormous thrust from a relatively compact nacelle. The GE90-76B, the launch engine, produces 76,000 pounds of thrust. To put that in perspective, a single GE90 generates more power than all four engines on a 707 combined. The fan diameter is 128 inches. You could fit an entire F-16 fuselage inside it. This created bizarre engineering challenges. The fan blades are so large that centrifugal forces during rotation create stresses equivalent to hanging a double-decker bus from each blade tip. GE had to develop entirely new composite materials just to keep them from tearing themselves apart. The combustor operates at temperatures that would melt conventional metals. The turbine section spins at speeds where material failure would send shrapnel through the nacelle, like shrapnel from an explosion. And it all has to work flawlessly, because if one engine fails over the Pacific, the other one becomes the only thing between 300 passengers and a very bad day. The 777 has 6 separate hydraulic systems. 6. Most aircraft have 2 or 3. 3 independent electrical generating systems with battery backup and a ram air turbine that deploys if all else fails, a small propeller that drops into the airstream to generate emergency power. The APU, auxiliary power unit, can be started in flight, something previous designs couldn't do reliably at altitude. Fire suppression in the cargo hold. 2 independent systems, either capable of handling a fire alone. Flight controls. Fully fly-by-wire with mechanical backup. If all computers fail, pilots can still control the aircraft through a direct mode using cables and hydraulics. Every system is designed so that any single failure, or even 2 simultaneous failures, cannot prevent safe flight and landing. This is the requirement. but proving it is another matter entirely. FAA observers watch as Boeing engineers deliberately fail systems mid-flight. They shut down engines over remote areas. They simulate electrical failures, hydraulic leaks, fire warnings. The aircraft flies routes that simulate the worst-case diversion scenarios: maximum payload, high altitude, single engine, deteriorating weather at the diversion airport. One test requires flying for 3 hours on a single engine, simulating a failure shortly after passing the equal time point on a trans-Pacific route. Pilots report the aircraft handles it easily. The remaining engine has enough power. Fuel reserves are comfortable. Systems remain stable. Pilots' unions in Europe raise concerns. Some safety advocates argue that ETOPS is a cost-cutting measure disguised as progress, that flying 3 or 4 engine aircraft is inherently safer, and no amount of testing changes basic arithmetic. If each engine has a 1 in 50,000 hour failure rate, 4 engines give you 4 chances to lose 1. 2 engines give you 2. Boeing's response is counterintuitive and statistically sound. You're calculating the wrong risk. A 4-engine aircraft is more complex, more systems that can fail, more maintenance points, more chances for human error during servicing. When you analyse total system reliability, not just engine-out scenarios, the simpler twin-engine architecture often proves more dependable. One revealing statistic: the 767, operating under ETOPS for nearly a decade, had fewer incidents requiring diversions than comparable 3-engine aircraft of the same era. Why? Because the obsessive redundancy required for ETOPS certification created aircraft that were over-engineered for reliability in every system, not just propulsion. Normally, airlines build operational history first, thousands of hours proving reliability in regular service, then apply for extended ETOPS limits. Boeing wants the 777 certified from day one. United Airlines has routes planned. Cathay Pacific has orders pending for ultra-long-haul routes. If the 777 launches with standard 60-minute limits, it's economically uncompetitive against the A330. The FAA is in an impossible position. Approve it, and you're trusting predictive modelling over operational history. Reject it, and you're potentially killing a program that represents the most advanced reliability engineering in aviation history. They compromise: ETOPS 180 certification, but with conditions. Additional monitoring requirements for the first year, mandatory data reporting on any anomaly, enhanced maintenance intervals. Boeing and the airlines must provide monthly reliability reports. It's certification with a safety net, and everyone knows the program lives or dies on what happens next. June 7, 1995. United Airlines flight 921, London Heathrow to Washington Dulles, a 777 loaded with passengers, crossing the North Atlantic under ETOPS 180 rules. Aviation journalists are watching. Regulators are watching. Airbus is definitely watching. The flight is completely routine, which is exactly the point. Over the next 6 months, the 777 compiles an operational record that silences most critics. In-flight shutdown rate, 0. ETOPS-related diversions, 0. Major system failures, 0. The reliability numbers are so good they're almost suspicious. Boeing has to provide additional documentation proving they're not cherry-picking data. By 1997, the 777 receives ETOPS 207 certification. Some variants eventually achieve 330 minutes, 5.5 hours from the nearest runway. Routes that were theoretically impossible for twins become routine. Los Angeles to Sydney, Dubai to San Francisco, London to Perth. The 777 doesn't just compete with 3-engine aircraft, it kills them. The DC-10 and MD-11 programs end. The Lockheed L-1011 is already gone. Even Boeing's own 747 sees order rates collapse for passenger variants as airlines realize they don't need 400 seats. They need 300 seats flying more frequently with better economics. The A340, Airbus's four-engine answer to ETOPS concerns becomes a commercial failure despite being an excellent aircraft. Airlines simply don't want four engines anymore when twins are allowed everywhere. By 2005, over 75% of new long-haul wide-body orders are twins, 777s, A330s, and eventually 787s and A350s. The entire architecture of long-haul aviation has shifted. But then, June 2016, Egypt Air Flight 804, an A320 crashes into the Mediterranean. May 2014, Malaysia Airlines Flight 370, a 777 vanishes in the Indian Ocean. Both incidents reignite questions. When aircraft fly routes where diversion airports are hours away, what happens when things go catastrophically wrong? An engine failure, the 777 can handle. But a fire, rapid depressurization, flight control malfunction? The ETOPS regulations assume a single-point failure, that the crew has time to assess, decide, and divert. But what about cascading failures? What about scenarios where 90 minutes to the nearest runway is 90 minutes too long? Modern turbofans are so dependable that engine-out scenarios are almost non-events. Pilots train for them constantly, but most will never experience one in their career. The GE90, Rolls-Royce Trent, and Pratt & Whitney 4000 series engines that power various 777 variants have in-flight shutdown rates below 1 in 100,000 flight hours. That means a 777 engine could run continuously for 11 years before statistically expecting a failure. The obsessive focus on redundancy, the triple hydraulic systems, the backup electrical generation, the fire suppression, created aircraft that are genuinely more reliable than their predecessors. Statistically, you are safer on a 777 crossing the Pacific than you were on a 747 flying the same route in 1985. But the question that remains, ETOPS doesn't eliminate risk. It redistributes it. You're less likely to have an engine failure. But if something goes wrong, something beyond the certified failure scenarios, your options are limited. A 747 flying with four engines has more than propulsion redundancy. It has routing flexibility, the ability to divert to less capable airports because it can handle short runways with asymmetric thrust, the ability to continue flight with multiple system failures because there's simply more aircraft. The 777 is elegant, efficient, and brilliantly engineered, but it achieves that efficiency through optimization. And optimization always means trade-offs. Air Transat Flight 236, 2001. An A330 runs out of fuel mid-Atlantic due to a fuel leak. The crew glides powerless for 20 minutes to an emergency landing in the Azores. Everyone survives. They made it because a suitable runway was within gliding range. On some 777 routes, like Fiji to Los Angeles, there are segments where the nearest runway is 3 hours away at cruise speed. If a similar fuel leak occurred there, you're not gliding for 20 minutes, you're going in the water. Today, every major long-haul route is flown by twins. The 777, A350, 787, A330. These aircraft dominate the industry. The last passenger 747 was delivered in 2023. The A380 production ended. Four-engine airliners are effectively extinct outside of cargo operations. And the safety record supports this. Statistically, ETOPS works. But it works because of something the regulations don't explicitly state. ETOPS succeeded because Boeing and the airlines took it seriously. The over-engineering, the obsessive maintenance. The real-time monitoring systems that flag anomalies before they become failures. The 777 program spent billions on reliability, not because regulations required it, but because the entire concept only worked if the aircraft was genuinely bulletproof. Here's the concern some aviation safety experts quietly voice. What happens when cost pressures increase? When airlines push maintenance intervals? When manufacturers look to cut weight and complexity? The ETOPS rules are written, but the culture that made ETOPS safe, the excessive caution, the conservative decision-making, the assumption that redundancy matters, that culture requires constant reinforcement. Next time you board a 777 for a trans-Pacific flight, think about this. The aircraft carrying you was designed by people who understood they were breaking a fundamental rule. That they needed to be better than the standard, not just meet it. The engineers who built the GE90 knew that if their engine failed at the wrong moment, hundreds of people might die. So they built it to standards that exceed any regulatory requirement. The pilots flying you trained for scenarios they'll likely never face, but train as if they'll face them tomorrow. ETOPS works because everyone involved acts like it might not. The moment that changes, the moment efficiency becomes more important than redundancy, or cost-cutting more important than over-engineering, that's when the mathematics of twin-engine ocean crossing becomes less comfortable.